there's nothing in the notes that go on discrete quantum walks. There's a book on, actually there's a couple books on discrete quantum walks, and I've put a link to a copy of Harmony Zan's PhD thesis, which is where most of the things I talk about will be. But I'm just warning you, so we'll be having probably 3.5 lectures on the discrete quantum walks, and that material is not covered in the notes that Gabriel and I wrote. Okay. So anyway, just to continue from where I left off, I was talking about average states, and I wanted to make a comment about the average. Introduce the average mixing matrix. So I defined the mixing matrix, more or less the first lecture, to be this guy, the shear product of the unitary matrix with its complex conjugate, or with its inverse, same thing. And so that's the matrix. The entries are non-negative real numbers. Each row in a column comes to 1. And it describes everything that you can observe by the result of measurements. Okay, so in some sense, you don't need to worry. If you have, there's nothing in, you don't have access to anything in U which you don't see in MFT. Now, the expanding U of T using the spectral decomposition, we get this with shear products of the R's. Now, it's worth remarking that you saw that the shear product of two positive semi-definite matrices is positive semi-definite. This is Scher's theorem. So these guys are positive semi-definite, okay? Whether it's ER circle ES or ER circle ER, they're positive semi-definite. And now we define M hat the same way we define the average states. So we just integrate, take that average. And when we do the integrate this term by term, the off-diagonal terms go away, and so we're left with this sum. So now this is positive semi-definite. This is a sum of positive semi-definite matrices, so M hat is positive semi-definite. Now the mixing matrix is not in general positive semi-definite. I don't know what it is, it's just a matrix. Okay. Now the average mixing matrix is an average of the mixing matrix. So since the mixing matrix has rows and columns summing to 1 for all T, it follows that the average has rows and columns summing to 1, and they'll be non-negative. Okay. Now it's a kind of so the averaging argument I just gave you is perfectly fine. You can also try and prove it directly from the definition, which is, I think, a useful exercise. But so you can prove directly that this is row and column stochastic, and clearly the entries are non-negative because you're taking the shear squares of the idempotents. Okay. So the other thing which we don't really need, but it's interesting nonetheless, is despite what looking at small examples will tell you, this matrix M hat is actually a rational matrix. So I'm assuming we're using just a standard adjacency matrix, or it will pass into Hamiltonian, and nothing fancy, but M hat is a rational matrix. Basically, when you're working with the mixing matrix, you're assuming that your initial states are going to be the vertex states, D sub A, and you're going to measure on a standard basis. Okay, and your Hamiltonian is the adjacency matrix, or Laplacian, or sinus Laplacian. Now you can consider other cases, but we're not. Okay, and so it's a rational matrix. And you can prove that by basically it follows because the spectral idempotents as a set are closed under the Galois group. And so you wave this number theory at it, and so you get this rational matrix. The problem is that it's a rational matrix, but the terms in the denominator are very, very large. Okay, and so it's not obvious when you look at the small examples. There's some calculations in the notes. I'll leave it at that. Now, it turns out there's a close relation between the average mixing matrix and the average states. So I want to go through that. So the M hat is the gram matrix of the average states. Now, the gram matrix of a set of vectors is just the, actually I might as well do it. So we have a set of vectors where U1 up to UM. And the gram matrix, I better not call it G, it is a matrix whose entries are going to be I call it UJ. So it's the, we have an inner product space, we have M vectors in a product space, we get the gram matrix. Okay, now the ground matrix is quasi-semi-definite because you can always write it in the form, well, let's not use it, say n starred for some n. And we saw the matrices of this form were quasi-semi-definite, but you can write this, well, anyway, so they're well, there's possibly easier just to prove it's quasi-semi-definite from the definition that a matrix is quasi-semi-definite if Z starred MZ is non-negative. If you do that, you'll get that result. So the ground matrix is quite useful in many contexts, and the important fact is it's quasi-semi-definite. The rank of the ground matrix is the dimension of the span of the UIs, and that's useful sometimes. Anyway, that's the point then, is that that's the ground matrix. And so we've got the average states, which are density matrices, but they're sitting in an inner product space now with our matrix inner product. And so we can form a ground matrix. And the claim is that ground matrix is in fact just the average mixing matrix. And so, and here's the proof. So we're trying to compute so this is the entry of the ground matrix, the AB entry of the ground matrix. And so it's a trace of the product. And I've expanded the averages. So D hat's an average, I've got rid of the averages. So I've got those two sums. Now, when I multiply these things out, if I get an ER times ES, I get 0. So the only terms when I expand this, I only get the diagonal terms. And so everything is this form. The mixed terms all go to 0 because ER times ES is 0 if R is not equal to S. Okay, now the next thing I do is I'm working with vertex states, so I'm expanding my vertex states. D sub A is EA transpose, and D sub B is E transpose. And now the thing to notice here is that this stuff, which is in white and blue there, is just a scalar. Okay, so we can move that out. And the other point is that we can move, since we've got a trace here, we can move this ER up here. You get an ER squared, but then ER squared is equal to ER. So we can basically drop that. And now we move that the A up here. And so we get a product of two scalars. Okay. And so that finally, and when we do it, we get this sum. Okay. And since the ERs are symmetric, this is an entry of the average mixing matrix. Okay. So there it is. So there's a close connection between the average states, the average vertex states, and the average mixing matrix. Okay. The thing I want to prove next is that, well, the average mixing matrix has got a number of interesting properties. The one I want to prove is that two vertices in the graph are strongly cospectral if and if the corresponding rows of the average mixing matrix are equal. Now, if you don't like rows, you can use columns, but that does, of course, it makes no difference. So, so that we have a number. If you look in the notes, there's about half a dozen characterizations of strongly cospectral, but this is perhaps one of the more interesting ones. Now, the proof of this, well, if vertices A and B are strongly cospectral, then the average states are equal. And so then, since their mixing matrix is just a ground matrix of dA hat in a product something and dB hat in a product something, and since dA hat is equal to dB hat, the two rows are equal. So that's the easy part. Okay, the second part's kind of an exercise in using positive semi-definiteness. And I think that's largely why I've included it, because it's a little bit easy to underestimate how important it is. So so now we're dealing with the case that the A and B rows of M hat are equal. I think that looked more like so we start this. So this is saying that the two rows of M hat are equal. Now, if this is 0, then this is certainly 0. It's trivial. And now I can replace M hat by its sum of the Schur squares of the idempotents, and I get this. Now, the point about this is this guy is quasi-semi-definite. Okay, and so each term in this sum is non-negative. And so the only way it can be 0 is for each term to be 0. Okay, Now so now we get to play again. If this is true for a positive semi-definite matrix, if M is positive definite and X star MX equals 0, then MX is equal to 0. This is the sort of cancellation you wanted to do when you're in the undergraduate courses. You weren't allowed to. But if positive semi-definite, we can do that. So we include this. Okay. So what we've established is if two rows of M hat are equal, then for any square of a Schur idempotent, for any square of the matrix idempotent, the corresponding rows are equal. Okay. And then, well, I'm not going to work through the details here, but then, okay, so then this gives you a little bit of work that the two rows, the A row and the B row, or the A column and the B column of E sub R, differ most in sign. Okay, so it doesn't take long, but you're using positive semi-definites in two different ways, and then you're using Cauchy-Schwarz, which is in some sense a consequence of positive semi-definites. Anyway, the easiest way to prove Cauchy-Schwarz in general for complex spaces is to write down this matrix. Now that's a Gram matrix because it's a matrix of inner products, and so it's positive semi-definite, and so its determinant is non-negative. And when you expand the determinant, you get x comma x times y comma y minus x comma y squared is non-negative, and that's the Cauchy-Schwarz inequality. The proof that you usually see for the reals over the reals using quadratic polynomials doesn't work for the complex numbers. This works in any vector space or in a product space. So you can view Cauchy-Schwarz as an application of positive semi-definiteness. And the only minor challenge is to verify that if this determinant is 0, then x and y are parallel. But we don't need that today. Okay, so we have the average mixture matrix. It is the Gram matrix of the average states. It's rational, and we've established we can read it off when two vertices are co-spectral. Okay, if the rows are equal. Now you can't have all the rows being equal, because in that case you would have a graph with all vertices being strongly co-spectral, and we can show under certain conditions that implies the graph's got almost two vertices, but we won't go there. Although I've stated here that there's can be shown that if the rank of the average mixture matrix is 1, then X is K1 or K2. And it's an open question which a bunch of us have bashed our heads at over an extended period, whether there are infinitely many graphs X such that with the average mixture matrix has rank 2. There are examples now known up to graphs on 64 vertices, 64, 32, and some smaller ones. It's not at all clear to me whether there are infinitely many such graphs or not. I'm inclined to think there might be, perhaps, but there's nothing like a proof known. Okay, so that's my short treatment of the average mixing matrix. You'll find more about it in the notes. And so, any questions then? Okay. I guess the other thing I should remind you is next week is reading week in Ontario, so there's no lectures next week. Okay. I'm going to start talking about discrete walks today. We've seen we have continuous quantum walks, and if you've got a continuous quantum walk, you've got a choice in Hamiltonian. It's common to use the adjacency matrix. You can also use the Laplacian or the sinus Laplacian, and the behavior is much the same in each case. There are differences, but it's there's in some sense they're differences of scale and not differences of real behavior. But in addition to continuous quantum walks, there are also discrete walks. Okay, now discrete walk is easy enough to find. We have a state space, a complex inner product space, and an initial state D, which is a density matrix. And now we're given a unitary matrix U, we can form a sequence of states. by taking u to the k, d, u to the minus k, we get a sequence of states, and that sequence of states is the discrete quantum walk. Okay, and it's just definition. There's no arguing about it. It's that sequence. It's it's a natural enough thing to do. If you think about it for a little bit, if you have a continuous quantum walk, and you look at the powers of U1, then sitting inside that continuous walk, there's a discrete walk. If you just shut your eyes and only observe at integer times, then what you're looking at is effectively a discrete walk. Okay, now that's not really a help to anybody, but it's just pointing out that they're there. They're not particularly unusual. Now, there's two general remarks. The first is there's actually a lot more varieties of quantum walks. There are continuous walks, so you can find different models of discrete walks, and they behave differently. And secondly, the quantum walks, the discrete walks, are on the whole harder to work with than the continuous walks. Now, a lot of the theory we've done about average states and things like that will carry through, and real states will carry over to the continuous case. And you can get things like perfect state transfer, but you don't get for a continuous walk. If we have transfer from A to B, then we also get transfer from B to A. That does not hold for discrete walks. So they lose some symmetry. That's one reason why dealing with them is more complicated. There are other reasons. Now, so we have our sequence, our discrete walk, and we get information out of the system by measurements as before, and in quantum computing they always measure with respect to the standard basis, nearly always, and so we just get the usual. There's no real surprise there. So that's the state at time k, and you take the inner product of your state with the terms of your P over M, and they give you the probabilities of observing the ith outcome. Okay, so from that, so there's not that much new there to worry us. The difficulty in practice is if you're trying to actually do computations with unitary matrices, then by n unitary matrix has n squared entries, and so if you've got 100 by 100 unitary matrix, you've got a 10,000 entries to fill in, and so it starts to get a bit expensive. And so the quote is essentially that you can't implement every unitary you want; it would take too long. So the unitaries you can implement, there's form a special set. So if you've seen any quantum computing and you've seen them talk about gates, well, those gates are just unitary matrices. And so when they're trying to work out their set of gates, they're trying to work out a small set of unitary matrices which they can use to do most of what they want. So they get all the other unitary matrices as products of the ones they already have. So the point is a gate is just a simple unitary matrix. And so when you have a set of gates to do quantum computation with, you've just got a set of unitary matrices. Now, as they're expensive to implement, and one idea is to simply express U as a product of simple operations. And for us, the simple operations are going to be reflections. Okay. This is what I'm going to turn on next. Okay. Now, it's not necessary for your unitaries to have that form, but in a large fraction of the examples that people work with, they do have that form. So excuse the pun there. So I need to talk about reflections. Now, one thing with discrete quantum walks is that a lot of the time we'll be working over real vector spaces rather than complex vector spaces. And in particular, the main example I work with is you're working over the reals. Okay, so when I talk about an orthogonal matrix, then I mean a real orthogonal matrix. Okay, now you can do this over the complex inner product spaces, and I'll say a little bit about that. But the point is that the basic example, which you use to implement Grover's algorithm, works with real matrices. This can be a bit of a shock to your audience sometimes when you're talking, because they sort of think if it's physics, you've got to be using quantum, everything's got to be complex. And it's not always true. You can get all the weirdness of quantum mechanics working with real vector spaces and orthogonal matrices. You don't have to be using complex states and complex unitaries. Any questions at this point? So the issue is here that, as I said, for discrete walks, there are a number of different models. Okay, and as far as the physicists are concerned, they're not interested in forming a catalogue of what's possible. They just want to get a few things which are easy to implement and let them implement things like Grover's algorithms or things of that type. So they're not too fussed about getting an optimal choice. They just want something which works well enough. And so you need to keep that in mind sometimes when you say, why are you working with this? Well, the answer is it's good. It does the job. Okay. Now, you do get to mathematical questions, and then that gives you a different framework. But the point in physics is that, as I said, there are several different models, the discrete quantum walks, and the physicists don't usually bother to make any. They tend to ignore the distinctions. Okay. A reflection anyway is an endomorphism of vector space that fixes each vector in some subspace U0 U and acts as multiplication by -1 on the orthogonal complement to U1 to U. So I need the inner product because I need to be able to define the orthogonal complement. Okay, so I can't define a reflection on an arbitrary vector space. I can define involution a map of order 2, but a reflection I require an inner product space. That's all right. We're just going to be using R to the n and occasionally C to the n. So if you have reflection, then if it fixes each vector in U0 and multiplies everything in the complement by -1, then the square of the reflection fixes everything. It fixes everything in U, it fixes everything in the complement, and therefore it fixes everything in the entire vector space. So any reflection has multiplicative order 2. Okay? So the simplest examples of reflections are the diagonal matrices with the diagonal matrices 1 and -1. Now the eigenvalues of an involution are always 1 and -1 because the minimal polynomial is t² -1. And so if the minimal polynomial is t² -1, your matrix is either I minus I, or its eigenvalues are 1 and -1, and has both. So these are the simplest examples, but in a certain sense, every reflection is similar to one of these matrices. And this is actually fairly easy, but every reflection is an orthogonal matrix that preserves the inner product. Okay, so it's in other words, reflections do what you would expect. Okay, now we're taking reflections in an arbitrary subspace U0. In the literature, in context of Cox groups and things, they're often looking at reflections which fix a hyperplane. And I'll talk about that briefly, but so sometimes when people say reflection, they mean reflection in hyperplane, but we don't mean, in this case, here we don't. Reflection is exactly what I've written here. Okay, so there's the conditions for reflection. And so reflections are orthogonal, they preserve length. And so that means, well, they're unitary, and so we can use them as transition operators for quantum systems. And we will be. Now, I thought I'd say a little bit about the complex case. We won't actually be using it. The definition of reflection on a complex vector space, it's a little bit uptight. There's a bit of argument involved, but the one I'm going to use is there's a subspace U0 in which it acts as the identity and acts as multiplication by an nth root of unity on the orthogonal complement. So if it operates like a square root of unity, it's pretty much the previous definition. You don't require it to be a square root. Okay. Now, this definition is probably not the first one, well, certainly would be the first one I would come up with, but it works. And it turns out that the interesting things that happen for reflections in hyperplanes carry through to reflections, complex reflections in hyperplanes in this case. So there's some justification for doing it. But so although this, now we're not worried about, so it acts as multiplication by an nth root. We're not forcing, we're not insisting that everything have the same m. Okay, just that it's an nth root. So it has finite order on the complement. Now I'm going to describe a construction. So we pick. I'm going to pick my reflection is going to be built using a vector A, which will soon be a unit vector. Yeah, that should be. I think I'm just putting in. So it's a unit vector, and we're defining a map tau sub A from U to U by this rule. Okay, so I'm choosing theta to be a K-through unity. So you could certainly think of theta being -1, and this would just be then 2. That would work. Okay, now okay, I've defined this. The first thing to notice is it's a linear map. And the easy way to do that is to say, well, the sum of two linear maps is linear, and the identity map that takes u to u is linear, and the map that takes u to this is linear. And so it's the sum of two linear maps, so it's linear. Okay. The other thing you see, it clearly fixes a perp. If you're orthogonal to A, if you use orthogonal A, then this is 0, and so you're acting as the identity. So it fixes a perp, and on whereas if you apply it to A, you get theta times A. So it's acting by multiplication by an absolute unity. So this would be a reflection in a height plane. This would be the complex version. Now, we don't really care about the complex. If you don't care about the complex version, you just take K to be 2, and everything goes through, you get reflection in a height plane. Okay, so I didn't write it down, but I will write it in now just as a, so in the real case, is equal to u. So my point simply is that you can you get a reflection in the real case, and so this is my second family of examples. The first family of examples I gave you were the diagonal matrices. This is a second family of examples. Okay. So there are reflections around. Now we'll see another construction, which is in some sense a generalization of this, but anyway, we'll see another construction which will be more useful for us shortly. And now, so the first sentence here is just saying what I just said, that we can get a real reflection, but we don't need that. Oops, excuse me. So we're really starting here. Now, I'm giving you now a third way of constructing orthogonal maps. I'm starting with an orthogonal projection onto some subspace. Well, actually, probably not. It's an orthogonal projection. It's mapping u to u, and it's an orthogonal projection. Okay. Now you just do a quick calculation. Then 2p minus I squared is equal to I. And so 2p minus I is a real reflection which fixes the image of p. Because if p little u is equal to u, then when you apply 2p minus I to u, you get 2u minus u, you get u. So it fixes MP and acts as -1 on the kernel of u, on the kernel of p. And so if we have an orthogonal projection, then we get a real reflection. Okay, and so we have a choice in a certain sense. We can go, if we want to, we can use the well, right here. Yeah, if you can also reverse the process, if R is a reflection, its eigenvalues are 1 and -1. So we add the identity to it. Now the eigenvalues are 0 and 1. So if we divide by 2, the eigenvalues are 1 and 0, and it's a projection. So in a certain sense, we have a sort of a group theory way of looking at it. We're saying this is a matrix that's got order 2, and it's an orthogonal matrices, and orthogonal matrices form a group, but you can also associate the projections. And so we'll be using both descriptions. Now, the one particular case that's going to be important for us is that if we take the all-ones matrix and scale it by divided by it, n by n or ones matrix, then this is a projection. It's a projection onto the space of constant vectors. Okay, and the associated reflection is given by this 2j minus I. Okay, Now, this plays a role in Grover's algorithm, or analysis of Grover's algorithm. And so the matrix or the reflection this is often referred to as a Grover coin. And I'll be doing that. So that's just a piece of terminology. So you can view this as a threat. We're going to be talking about Grover at some point, I hope. And in that case, we deal with Grover coins. Okay. Any questions at this point? Now, in fact, one reason the connection to projections is useful is because we can, in a sense, construct projections combinatorially. And so that's what I want to do now. Okay, so I've told you what reflections are. Okay, and really, and I've said that they're related to. So I said we have reflections. If P is a projection, 2P minus I is reflection. This process is reversible. That's what we're saying. Okay. We've got the Grover coin, but that's just giving something a name. Now, how are we going to construct the predictions we use for quantum walks? So I'll describe how we do that. So we start with a finite set. Now, a partition of that set is a set where each element is a subset, so that these subsets are pairwise disjoint, and the union is order V. I was too lazy to write it in, so I don't think you really need to be told what a partition is in any case. So it's a set of so the elements of a partition, I usually call them cells. Okay, but so a partition is just a set. It's just that the elements no longer singletons, they're cells, and those cells are pairwise disjoint, and their union is the underlying set. Okay, so that's a partition. Nothing's changed there. The order doesn't matter. They're not ordered partitions. Now, I'm going to use whatever you want to call this to denote the number of cells in pi. It's standard notation for the size of the set. So the size of the partition is the number of cells. So that's standard enough. Now, because I like linear algebra, and I need to represent my partitions with matrices. And so now, normally, often you're dealing with sets, subsets of some set, and so you write down characteristic vectors. Since partitions are more complex structure, I'm going to need something to do a little different. So the characteristic matrix of the partition is the matrix with rows indexed by the elements of V and columns by the cells. And the ith column is the characteristic vector of the ith cell. So that gives you if your size of V times size of pi matrix, it's 0, 1 matrix. Each row sums to 1 because each element of V isn't exactly one cell. Instead 0, 1, that tells you that the columns are orthogonal, pairwise orthogonal. So the dot inner product of two columns is always 0. And so if I have a characteristic matrix M, then this statement here is just saying that the rows columns sum to 1. The other point is that if I take M transpose N, I get a diagonal matrix. Okay, and the diagonal entry, I've got M's and P's swapped around here, but let's fix it while I'm here. And the KK, the kth diagonal entry at M transpose is the size of the kth cell. Okay, so it's diagonal. It's often and more convenient to scale the columns so they have unit length. Okay, and then in that case, we get what I call a normalized characteristic matrix, and in that case, M transpose M would be equal to the identity matrix. Now, one reason that's useful is that if M transpose equal to the identity matrix, then M transpose M, the orders change. I square it, we get this. Whoops, didn't want to do that. We get this. And notice we've got an M transpose M in the middle, and because we've scaled things, that's now just an identity until we get M transpose. So that tells us that M transpose is idempotent, and it's also clearly symmetric, so it's a projection. So every we have a partition, the normalized characteristic matrix determines the projection. I've just told you how to get it. Now, of course, if I say something's a projection, you should ask, well, projection onto what? Well, if we let f of phi denote the functions on set V that are constant on the cells of phi, then M transpose is a orthogonal projection onto that space. In some ways, that's trivial, but it's just slippery enough that it might actually be worth putting in an assignment. So it is a projection. It's a projection onto the functions constant on the cells of phi. Okay. Now, this plays a role in things like equitable partitions and stuff like that, which are important in algebraic graph theory, which we won't be going into. So my point now is that from a partition, I get a normalized characteristic matrix, I get a projection, and then we remember, oh yes, from a projection, I can get reflections. And a large fraction of the quantum walks that people use, the unitary matrix is given as a product to reflections, and the reflections are given by two partitions. So sometimes I have weightings as well, but we won't be going there. I'm just going to give two examples, okay, that have actually we've actually worked with. So the first one, so what I'm going to do now is I need to construct pairs of projections because I want to get two reflections. And then I'm going to say the product of those two reflections is going to be my transition matrix. Okay. Now, okay, so let's think about it. So I'm going to take a bipartite graph with a bipartition into two parts, left-hand side and right-hand side. So now I said I have looking at a partition on V. That's slightly unfortunate because in this case, V is going to be the edges of this bipartite graph. So we're looking at partitions. So we're taking the edges of our bipartite graph and looking at partitions of those edges. Okay, and there are two obvious ones. I'm going to call the first partition pi L, and its cells are the edges that contain a given vertex on the left. So if one's on the left, then all the edges that contain one form the first cell, C1, if you want. Okay, so that gives me a collection of cells. Those cells partition the edges, and no edge lies in two cells because we're bipartite. Okay, and okay, that worked. So we can do the same thing on the right-hand side, and we get a partition pi R. Okay, now we don't really need this, so I'm not going to if you have two partitions, the collection of partitions of a set form a lattice. And so they have a meet and a join corresponding to the intersection and the union. Now the meet is easy enough. It's just a partition you get by taking the intersection of cells of the first partition with cells of the second. There's also a join, which is a little trickier to define, so I'll leave that. And in practice, when we're working this setup, we usually want to choose our two partitions so that the meet is the discrete partition where every cell has got size 1, and the join is the entire set of edges. Okay. In practice, this will look after itself, which is why I'm not going through it. So the point is, for a bipartite graph, I get two partitions of the edges. Okay, and so I get two reflections. Okay, that gives you a discrete walk, which with no originality being wasted, it's called a bipartite walk. There are also weighted versions of this, but Will Harmony and Tina both worked on bipartite walks. For the second example, it's related. We're going to construct partitions of the arcs of a graph. Okay, so an arc in a graph is an ordered pair of adjacent vertices. Okay, so if the graph's got m edges, it's got two m arcs. So what are our partitions? The first partition is sometimes the obvious one. You just take the cells are just pairs consisting of AB and BA, where A and B are adjacent. So you get cells of size 2. It's a pair of opposing arcs. Okay, so if there are m edges, you get this partition's got m cells. Okay. In this case, the reflection is just the obvious map that swaps AB and BA. So it's permutation. I'll say that again shortly, I think. The cells of the second partition are the are the sets of arcs that contain a given vertex of the graph. So they're the arcs leaving a vertex. And so that gives us two partitions. And as I said, the meter of these two partitions are discrete, and if the graph's connected, the join has just one cell. In practice, we'd be assuming the graph is regular and connected even. And this gives you, okay, so now I've got two partitions, I've got two reflections. This gives you the arc reversal walk. Now, that is in some sense the simplest useful quantum walk, and can be used, as I said, to analyze, to describe Grover's algorithm and to analyze it. Okay, so and so now the bipartite walks are interesting in part because the structure, if you pick your bipartite graph, it's natural to assume that it's an instance structure of some graph. Okay, instance structure of something, so it could be the instance matrix of a predictive plane. Okay, and now you go through it and you get a walk, and the structure of your walk depends on the will depend on the underlying geometry. So there's a connection between the combinatorial properties of the underlying set and the walk. But we won't go there. Now, the final comment here is that to notice that there are many classes of discrete walks which do not arise from pairs of partitions. Now, it's actually well, officially any unity matrix gives you a discrete walk. The problem is at some point you want to do some analysis, and that means you start needing spectral decomposition and eigenvalues and eigenvectors of U. And so there's not much use coming out with a model of a quantum walk where you can't carry out that calculation. Okay, now, and so it turns out the two reflections, so you have two elements, R and C, R squared equals C squared equals identity, that will give you a useful quantum walk. If you take R squared equals C cubed equals the identity, well, that will give you a quantum walk too, but I don't know I have no idea how you would compute the eigenvalues and eigenvectors and do them. Okay, so the reason what restricts us, in some sense, are two things. You have to be, you want to be implementable, and you want to be able to carry out the analysis. Now, it turns out that the two reflections walks give us examples of these, they give us useful things where we can do the analysis, and so it's interesting to investigate. Now, let's say a little bit about the arc reversal walk. Yeah, okay. So the general assumption with the arc reversal walk is you assume the graph is regular. This is not strictly necessary, but the regular case is enough to do what's interesting, and so why make your life more difficult? So at k regular on n vertices, so the number of arcs is n times k. The state space for the arc reversal walk is the space of complex functions on the arcs. So that is a complex space. You can think of it as c to the n k, or you can also think of it as c to the n tensor c to the k. The first reflection is the reflections are coming from the two partitions I just gave you. There's protections on the arcs, and so you have R maps AB to BA for each arc BA. So R is symmetric and R squared is the identity. So that's your first one. For the second reflection, we're going to specialize a bit. We'll start with a k by k unitary matrix of order whose square is the identity. And in most cases, this will be 2-1j minus I. And this is called the Grover coin, as we noted earlier. And now our second reflection is just it's just a diagonal matrix with copies of G down the diagonal. Now this does correspond to the partition of the arcs according to their starting vertex. Although Harmony and I are always arguing that which is the head, which is the tail of the arc. I don't want to go on that. The other thing, if you're symmetric in order 2, you're orthogonal. And this has got order 2, so the whole thing's got order 2. So I don't need the partition to write this down. Now, once you do this, okay, so now I've got an operator R reflection and a reflection C. So now, and so then I take my unitary to be R times C, and there's my arc reversal walk. Now, the comment I want to make, of course, if you stirred this a bit, you realize, well, there's nothing, you don't have to use the growth of coin. You don't have to use the same coin on each block. So you've got lots of choices. Now, if your choice gives you something which is not involution, I will leave you to compute the spectral decomposition because I don't know how to do it. Okay. So anyway, leaving that as is for the moment. And so we have defined R, we've defined C, and the product RC is our unitary. It's actually an orthogonal matrix working over the reals. And the problem is to determine the eigenvalues and eigenvectors of U. And so what we're going to do is that we're going to see that these things are actually, these things that you might hope are actually determined by the spectrum of the underlying graph, but we have to work fairly hard to get to that point. So the next step would be to worry about the eigenvalues to start with thinking about that, but I'm not going to do that at this end stage of the lecture, so I'll stop there. And I remind you again, no lectures next week.